Good morning, students. Today we will continue with Unit 1, Introduction and Water Applications, Topic 4, Water Application Methods. Water Application Methods, Surface Irrigation. It is where water is applied and distributed over the soil surface by gravity. This method is further classified into flooding. This is further classified into the following. 1 is free flooding and 2 is check flooding. Free flooding, it requires the field to be properly graded with a very small gradient, almost flat, a large source of water, minimum labor, no particular construction, no wastage of land for laterals, etc. However, its water efficiency use is lowest and the upper field gets almost 3 to 5 times more water, while the lowest field may get insufficient quantity. Number 2 is check flooding. Here, the surface flow is checked, that is, controlled by levees, constructed parallel to flow direction or along the contours and across it, with the plot enclosed by levees is made horizontal. This method has higher use of water efficiency, close control of the farmer, less amount of deep percolation, and can be used for better variety of crops. This is suitable for many crops like rice and any type of soil ranging between permeable sandy loam to clay soil. The defects of this method are more investment on construction of levees, continuous attendance for operation, obstruction to farm machines, loss of cultivable land under levees. Number 3 is border strips. This is the best method amongst flooding because of the efficient use of water. In this method, the field is divided into strips of 3 to 20 meter width by low embankment called borders. Furrows and corrugations. A furrow is a channel of very small cross-section, trapezoidal, parabolic, or semicircular in shape, dug or made between the rows of crops. The crops are shown on ridge between two furrows. A corrugation is similar to a furrow, except that the depth is less and spacing may be more. Furrows are provided one per row of crop or per two rows of crops like maize, sugarcane, cotton, etc. Furrows are classified as straight furrows, contour furrows, level furrows. Straight furrows, it is aligned along predominant slope in the field and the field slope should be flat. Furrows are aligned normal to the supply channel and bed slope is almost same as the land. Contour furrows, it is aligned along contours in the farm having ground slope steeper. The furrow bed is given very gentle slope so that erosion is avoided. Level furrows, these are the furrows having no bed grade either in contour or straight alignments. Following water is blocked by obstruction across such furrow and is made to stand still to the holding capacity of the furrow. Subsurface irrigation. Sub-irrigation is the process of applying water to the crop root zone from below by controlling water level within the soil under favorable conditions. Drip irrigation. Drip or trickle irrigation, it deals with the supply of water to the root zone by emitting drops of water very near to the ground surface and the plant stem, that is, water trickles from the emitter. The frequency and size of drop depends upon the type of soil, type of crop, growing stage, season, etc. At present, this method is adopted for gardens, cash crops, and may be adopted for root crops as well. This is a figure showing furrows. Sprinkler irrigation. This is an overhead method of irrigation application in which water is sprinkled from above the crop, simulating rainfall in the form of fine jets or sprays. This method is adopted generally under all circumstances, particularly where the water is scarce, soil is permeable, and terrain is rough. But this method is not suitable where the wind blows at more than 15 km per hour. The soil has very low permeability. This is a figure of sprinkler irrigation. This figure shows twin nozzle rotating head. There are four groups of components. They are number one is pump, two is distribution pipelines, three is risers and sprinklers, and four others. Pumps. A pump is required to lift water from the source at the designed rate and to increase pressure. Pumps that are operated on electricity or diesel and either centrifugal or deep well pumps are commonly used. Engine of a tractor can be used as prime mover for the pump. Pumps may be fixed in position or mounted on wheels to make portable. Number two is distribution system. The distribution system, it comprises of A main and B laterals. The buried mains have advantages like non-interference like farm activities, no loss of land, less annual cost, and longer life of pipes. However, the installation cost is very high. The laterals are usually black PVC pipes, 3 to 5 centimeter in diameter to 5 to 12 meter by length. These are connected to risers. Sprinklers. It is mounted on risers and are of three types as fixed head, number two rotating head, number three perforated pipes. The fixed nozzle types are not in vogue. It consists of nozzle mounted on holes made in the laterals and can spray in 135-degree zone with 15-meter radius. The rotating head, it is shown in the figure drawn above. The rotating head may be with single nozzle or with twin nozzle. The head rotates about vertical axis by the action of jet through the driving nozzle. The jet impinges on the deflector, moving it to one side, but the spring tries to set it back, which is restricted by a stud mounted on the body, causing the body to rotate slightly. The action is continuous, causing full circle rotation. The rotating heads are in common use. A single nozzle can provide slow dose while the double nozzle cannot. The heads rotate very slowly. Their jet sizes are large and hence changes of clogging are reduced. The pressure requirement varies between 200 to 700 kilopascal. The fixed head and rotating sprinklers are mounted on risers 30 cm height to 2.5 meters and are spaced 5 to 15 meter center to center according to the requirement of planted crops. Students, I will conclude my lecture for today by showing you a video.
furrow irrigation, we want to be as efficient as possible. And the things we look at are the distribution of the water through the field, which is affected by the hole sizes in the tube, the white tube. Also, the soil infiltration characteristics of how fast that water moves through the field and whether it can actually infiltrate. And also, we want to minimize tailwater when we're considering the distribution of water over the field, because water that runs off the field is taking nutrients with it, and it is not beneficial to that crop. And so we want to minimize as much tailwater by cutting off the well when it is appropriate. When selecting the hole sizes, you want to consider that you want to maintain the proper hydraulics through the white poly tube, so that you don't have pipe blowing up or not completely filling up. And you want to evenly apply that water across the field so that you have portions that are not underwatered while other portions are overwatered and having tailwater run off. There are 2 computer programs available to help you determine the correct hole sizes for your specific field. One of them is called Faucet. It was developed by NRCS quite a few years ago. It has been adopted by some other agencies that have modernized it so that it'll work with current Windows programs. An alternative to Faucet, which is still a little difficult to use just because it's not very user-friendly to the way we use computers today. So the alternative is Pipe Planner. It was developed by Delta Plastics. It's the same thing as Faucet, only it's very user-friendly for the most part. Point and click. You use Google Maps to select your field locations, your well location, drawing your pipe sets. It's going to select whether it's in the field or out of the field, of whether it should be supply line or it should be line that you're going to actually punch holes in. I mean, it has a lot of cool features and it's very visual. And so Pipe Planner is basically the new standard that has replaced Faucet. So if you are experiencing irrigation sets that are longer than 24 hours, because no agronomist will tell you to irrigate for more than 24 hours at once, because you're minimizing the amount of oxygen to the plant. If you have rows that water out at different times, if you have a pipe, which is the lay flat tubing, that is too full, very full and high pressure within that pipe, or if your pipe is deflating before it gets to the end of the set, or if you're having pipe that blows up and you need to make adjustments for that, Pipe Planner or Faucet are the programs for you. Even if you don't have these problems, it can still be beneficial. For example, both programs will output a expected watering time, which means if you are supposed to irrigate for 12 hours, then it will tell you this will probably take about 12 hours to water out. And with that number, which may need some adjustment and you consider the real world factors, can help you plan of when you need to go and shut off the well or switch an irrigation set. And so that kind of information can help you plan out your irrigation management, and you can get a lot more done during work hours and not have to get up at 3 a.m. to go switch an irrigation set or turn off a well because you didn't realize that was what was going to happen. You can also work with different pipe sizes. If your distributor carries 12-inch pipe and that's what you always used, well, you might be more efficient if you're using a 15-inch pipe or a 10-inch pipe, depending on your situation. And so you can play with those pipe sizes as well as the number of holes, whether you want to punch a hole in every furrow or every other furrow. The program can help you determine whether that's a better option for you based on the output. Another technology available is a surge valve. So you've punched the appropriate holes in the pipe, and now you need to move that water across the field. A surge valve can help you move that water across the field while infiltrating more efficiently. And so the surge valve, which has a little controller on it that will need to be programmed, will surge the irrigation to each side of the field. It splits the field basically in half, and you'll surge it onto the field, allowing time for infiltration. That removes the difficulties with those long irrigation sets where you're reducing oxygen to the plant. That gives time for the water to soak in before it reaches the end. And then you have better infiltration and more even infiltration along the length of the field. Here's a visual example of that. So this is a continuous large furrow stream, which is the typical way we irrigate. The white pipe at the head of the field is irrigating down the length of the furrow, and to get enough water within the root zone, you have a significant amount of deep percolation at the beginning of the field, as well as a significant amount of tail water that's running off the field and is very wasteful. With surge irrigation, you're still going to have some deep percolation. There's no way to really get rid of that with the length of our rows, typically. But by surging it and allowing water to infiltrate before you apply another amount of water will allow for more even infiltration along the length of the field, as well as have less tailwater at the end of the day. But it's going to take a bit more management to use a surge valve. One of the feedbacks we've had about surge valves is that they can be expensive, especially if you're using them in a lot of different fields. They can increase in cost very easily. In those situations, you can surge irrigate on your own by switching irrigation sets manually. That is definitely something that if you wanted to take on or had an irrigation manager that could take that on, that's definitely a possibility. And then you're only paying for the labor of switching those sets and not the valves themselves. Flow meters are another great technology that actually would be needed to run pipe planner or faucet well. It's actually the most important information you can have is from the flow rate of your water source. And so to know your flow rate, as well as to estimate how much water went to the crop, these devices can be put in line. There are different kinds of flow meters that fit your application, but these are the kinds that I use. They're inline propeller style flow meters. And so I determine the depth of water applied to the field by taking that volume estimate from the flow meter and dividing by the number of acres I irrigated with it. So in this example, the depth of water I applied was the flow meter reading, which was 163.82 acre inches, and I irrigated 60 acres with that amount of water. So I divide it by 60 acres, and my acres divide out, which leaves me with inches. And so I applied 2.73 inches of water to that field. Now, if I had my field, my flow meter measure in a different unit, for example, gallons, it just makes the conversion a little bit more difficult, but still very doable. So on that bottom line there, you'll see that my depth is equal to that number of gallons is 4.4 million gallons, which I converted to cubic feet using the conversion 1 cubic foot in every 7.48 gallons. And then I divide by the 60 acres, which I convert to square feet using the conversion of 43,560 square feet per acre. And then I converted the feet that I have left to inches using a very simple 12 inches per 1 foot conversion, which also gives me the 2.73 inches. So I arrive at the same depth of water applied to compare to rainfall or other areas that I'm going to use that number, using different ways to measure it. Okay, so now let's talk about smart technologies. A smart technology is something that helps you determine when to irrigate, as well as how long to irrigate. And there are many different ways to do this. And basically the idea is to help the grower make an informed decision about scheduling irrigation. And that is based on feedback from the crop's environment. So this is from, for example, a soil moisture sensor, from local weather and scheduling based on ET, or a combination of both. So let's focus on soil moisture sensors, because that's what's been used most readily in Louisiana in the last few years. There are multiple types of soil moisture sensors. The first one I'm going to discuss is the soil matrix water potential sensor, and that can be in the form of a tensiometer, which really isn't a sensor, but it kind of does the same thing as the sensors we're going to talk about. That is a tube there that is filled with a liquid, like a distilled water, and put under a vacuum, and the tube is buried so that the pressure gauge is sticking out of the soil, and it is going to, as the soil dries, water will be pulled through the clay and the pressure will increase on the pressure gauge. And so you can read that pressure every day and see how much water is leaving that soil. An alternative to walking to that sensor every day and reading it is to use a granular matrix sensor, like the Aerometer watermark, which is pictured on the bottom there. That sensor would be buried into the soil, and it would be connected to something that would either read or log the information. But it'll work on the same principle. The drier it is, the higher the number. It'll read in like a tension reading, like centibars. Pictured here is a little manual reader. And so if that sensor was buried in the ground in a field, you would walk out with that manual reader and clip up the wires to those alligator clips, and you would get an instantaneous reading. So that would be similar to using the tensiometer. There are loggers as well as telemetry loggers that will broadcast the information back to your computer, your phone, depending on the technology of what you want, which may be better options when you bury these in the middle of a crop field. Volumetric water content sensors are an alternative to the gravimetric sensors we just discussed. These sensors estimate soil moisture by estimating the volume of water per volume of soil column. And I'm not going to get into the details of how they work, but there are different kinds. What I am going to point out from these different examples is that some are individual sensors where you bury them in the soil however is most appropriate, and then it will still need to be wired to a logger or some sort of reading device. There are other sensors, such as these tube-style sensors, where there are multiple sensors within the tube, and then the whole tube is buried, and then those sensors can estimate soil moisture at multiple depths. Those sensors typically have software associated with them that you have to use. When considering picking a sensor, I would look into any recurring or annual costs, as well as the ease of use of the software. That's almost more important than the sensor itself. Okay, now let's talk about how we're going to use a soil moisture sensor in agriculture. So this is an exaggerated picture of a corn crop with a very dense root system that probably doesn't exist normally. And we are going to irrigate it, and that water will infiltrate into the soil. Now you can see that some of that water is interacting in the middle of the row, some of it is draining downward, some of it is running off still, but there are different amounts of water in different places in the soil, and that will eventually hopefully redistribute, but even if it doesn't, what you're going to be sensing will depend on where that sensor is in the profile. So for a watermark sensor, for example, we may bury 3 or 4 of those within that root zone so that we have different sensors to look at as the root system develops. And so when those sensors are very shallow, you'll care about those at the beginning of the season. But as the crop grows and becomes more mature, you may look at the 12, 18 to 24 range to make your decisions. And so you can see how in this example, those 3 sensors would read 3 different amounts of water, and they would all be accurate in that reading. The tube style sensor is very similar. You would bury it as close to the roots as possible. You can't always get right on the seed bed without destroying the crop above it, and it's important to have a strong root structure around the sensors. So just get it as close to the roots as possible. I usually offset mine off the middle of the row. But the sensors can come in different lengths. For example, this tube style sensor apparently goes to 40 inches, but it can have different lengths. You just pick what's most appropriate for your application. And so the same thing here, those sensors would read a different soil moisture depending on the depth of the sensor. And so when you're going to implement soil moisture sensors, one thing to consider is how they need to be installed. The watermark specifically has some rules with them. They have gypsum material inside, and so to properly use that material, it needs to be exposed to the full wetting and drying cycle before it is installed. So this is an example of how I did all of my sensors my first year when I went to install them. I created a grid on this Tupperware container and balanced the sensors in some water so that they would soak. And then I hung them for a couple days on my back patio so that they could air dry as much as possible before I installed them. Some sensors require very good contact with the soil for them to work properly. The watermark is one of those. The sensors that have the rods are a different type of contact, but it definitely needs good contact with that soil. So sometimes to get that contact, you need to make a soil slurry, which is an extra step in installing these sensors that should be considered. You'll need to select a good field location that's representative of what you're trying to achieve. And then you also want to make sure that you select a good logger location. For example, if you're going to use a logger that these sensors have to wire directly into that do not have telemetry, then you may want to mount that logger at the edge of the field so that when you go to get the information from the logger, you don't have to walk through the field to get to it. We've had difficulty when it rains, as well as with wild animals, when we've tried to get to our data loggers, and that really slows us down when we're trying to make irrigation decisions during the season. You also have to think about what depths are most important for when you install the sensor. The tube style sensors have a little different list of requirements when you're working on them, but a lot of them the same. You may still need to create a soil slurry. Some tube sensors don't need that, some do. You may need specialized equipment to install those sensors. You still need to select a good field location and then also consider the software associated with that sensor and what works best for you. So here's an example of an installation of individual volumetric sensors for one of our research studies. We dug a hole with an auger as well as a post hole digger to do the last bit. Then we installed our sensors into the sidewall of the soil. And that was our best way to get undisturbed soil to hopefully measure how water would move through the soil that didn't have a hole dug in it. Because once we fill that hole back in, water will move through it differently than the natural areas of the field. And we were trying to get away from that. There is not a sensor that exists on the market that doesn't need some sort of calibration. And so that is something to be considered when you're interpreting the data. What you're seeing here in these two graphs are the relationship between gravimetric water content and volumetric water content. Basically, the difference between the pressure reading and the volumetric reading, or the percentage reading. And both of these are showing interesting relationships between those two readings. On the left is the data we collected from some of our research, and it is showing that over a large range of soil water potential, we had very little change in volumetric water content. And this was on a sandy loam soil, so we would expect a lot more movement in the volumetric water content on the soil type to relate to that much range in soil water potential. So even though there is a relationship between those two, one of my sensors was not as accurate as it should have been and would need to be calibrated. On the right-hand side is an example from literature